Good afternoon. Can you hear me? All right. Want to make sure you can hear me. It shows that my mic levels are working. Excellent. Thanks. Any questions before we get started? So I was wondering if anybody would show up. So thank you. That looks like there is at least six or eight people that are on. So this is actually a pretty important lecture. So it's good that you are here. So we'll go ahead and get started. The test will be released. I knew that question was coming. So tonight or tomorrow morning. It will not be as long as the other ones. I don't intend it to be. All right. See here. All right. So today we're going to be talking about bolts, screws and fasteners, continuing to finish up that chapter. And we're going to be talking particularly about the preload and fastener, which is not necessarily super intuitive. And so I have a bunch of slides which I hope to make it a lot more clear so that when you design with bolts, and there's, as we said earlier, like over 2 million bolts in a Boeing 747, and they're used everywhere, then you will at least understand the preload and the importance of the preload against fatigue and other loads that you'll find in a system. Okay, bolts are primarily used to clamp parts together, and the bolt is put in tension. They're also experience shear. We'll talk about that later. But when we apply the bolt to the structure, what we're doing is applying the we torque the bolt down so that it gets up to close to its proof strength. And the proof strength of a bolt is it's about 90%. The proof strength is almost as large as the yield strength, but it's slightly larger. And it's the point where there's a permanent set, and that basically just means you've stretched the bolt and it's not going back to its original length. Okay, and so each type of bolt has its own proof strength, and when we and they're rated, so you can look them up on the bolt that you get. It'll have an associated proof strength, and the recommendation is to load the bolt, preload the bolt when you install it to 90% of its proof strength, and we'll get into the reasons for doing that. And that's for static loads. And then it's recommended to load it to about 75% of its proof strength for dynamic loads, for fatigue. These seemingly high loads make it unlikely that the bolts fail in service if they're selected properly for the application. So it's actually very important to make sure that the bolts are installed to the right load so that they are used as they were designed to be used. So these subtle details are really necessary to be understood. And here's just the typical terminology. So if you have a load on each side of a joint, then you have a bolt that's holding the joint together. We have the thread length, the overall length of the bolt, the length of the thread, and the length of the bolt. We'll show the other ones here. And the LS is the length of the unthreaded portion. Now, bolts and the materials that they clamp between them each have a stiffness. And so you can almost imagine that the material that's being bolted together is acting kind of like a spring. The bolt is almost always a lot stiffer and harder than the material that it's clamping. And you can treat the material being clamped, instead of like this material, you can think of it as a stop, okay? And so the way that a bolted joint works is that if you were to take a bolt and you were to pull it down with a load, and pulling this spring down, and insert a stop where you precisely had a certain load, in this case it's 500 newtons, and you put the stop in there and then release the load, then you have this clamping force here on the material, puts the material in compression, so that 500 newtons is experienced by this little stop. And what's important to note is if you apply a load then on that bolt, let's say 400 newtons, then you have 100 newtons in the stop. You still have 500 newtons in the bolt. Okay? And so what this illustrates is that when you apply a tensile load to a joint, that tensile load actually relieves the stress in the material, because the material is usually softer, and the bolt still has that preload value. Okay? So if you increase that to over the preload, then of course you'll get it to elongate and it'll pop off. Okay? So these are the subtleties of what's happening in a joint. There's another illustration. This is from Wikipedia. Basically says the same thing in a little bit different words. So in this case, they use a 1,000-pound preload. If you put 1,000 pound, then throw a stop in there, okay? And then if you put any external load on there, okay, the spring is not going to move. So you see this little scale here, okay? So if you pull it down to this tick mark, and then you install something here, like if you apply a load all the way up to that original load where you brought it down to this tick mark, this stress here in the spring stays the same. That means the bolt stress stays the same. And if you pull it further, of course, it'll pop out. Okay, so only when the external load exceeds that preload can you get that tension to increase in the bolt. Okay, this is what a bolted joint looks like. These are the forces here in yellow that are distributed throughout the bolt, and we'll talk about those as well. All right. So when we talk about a bolt or a joint, and as we just mentioned, they have their own associated stiffness. There's a stiffness associated with the bolt and a stiffness associated with the material between the bolt. Okay, as we saw before when we looked at axial loading at the beginning of the semester, we saw that the elongation is the force times the length of the bar in tension, divided by its cross-sectional area times the Young's modulus. If we rearrange this, we can describe, we know that the stiffness is the force over the deflection, and if we express that in terms of the deflection equation, then the stiffness is the area times the Young's modulus over the length. Okay, this is an important concept to remember. This shows up all over, and you'll see it if you take the PE exam. Okay. Since joints have different materials with different stiffnesses, you can get an effective stiffness by using the equation for springs that we saw in the spring chapter in series. Okay, so you can take 1 over the stiffness of each of the materials and get a total stiffness. Now bolts, they have different cross-sectional areas, different cross-sectional effective areas here where you have the threaded portion and where you have the unthreaded portion or the shank. Okay, and so we can express the bolt stiffness in terms of those two different areas. Okay, so we have 1 over the bolt stiffness is the length of the threaded part over the area of the threaded part times the Young's modulus of the bolt, which is going to be the same. And then we have this unthreaded part, which is L minus LT, which is this threaded part. And then we can express that in terms of the threaded length and the shank length, or this unthreaded length here. That's the LS. So therefore, we can express the bolt stiffness by combining these terms as the area of the threaded part times the area of the bolt that's not threaded, weighted by the lengths for each one, the opposite of each one, times the Young's modulus. And that way we can get the effective stiffness of the bolt. The standard threaded portion of a bolt, just for reference, is twice the diameter plus 1/4 inch. For bolts that are less than 6 inches, it's twice the diameter plus 6 millimeters for metric. Bolts longer than 6 inches have an additional thread length of at least 1/4 inch. Short bolts are often threaded all the way to the head. Okay, so they're often threaded all the way to the head. In this case, we have a cylindrical area. This shows a cross section of two cylindrical objects here. And so if we have this area here of these two cylindrical materials that we're joining, we can calculate their effective stiffness as well. And if we express it in terms of just that material, then we have an effective area and effective diameter that's of these cylindrical sections that load is transmitted through. Okay, so we can get an effective material stiffness. That's what the M is in this expression here. And it's just the length of the one material over its effective area and Young's modulus plus the length of the second material times its area and Young's modulus. If we express it in terms of the effective diameter, we can rewrite it in this equation like this. Now, if the material is the same, the Young's modulus of the materials is the same, then the stiffness of the material joint is just the area times the Young modulus over L. Okay, the effective area over the times the Young modulus over L. If it's cylindrical, as we have in this case here, then we have this equation for the area. Okay, so this is just the way that we calculate the stiffnesses, but obviously we don't bolt cylindrical joints together all the time, and usually we have continuous material, and we'll talk about that as well. And so, but first we need to talk about the actual load conditions in the bolt and in the material. Okay, the bolt is in tension, and the material between the bolt is clamped, and so it's in compression. The material is steeper. The material slope in this case is steeper because of its larger area. Okay, and what's shown here is the force per displacement line, and as you can see, we have a negative slope here, okay, and we have a positive slope for the bolt. So when the bolt and the material are in contact, the force is the same. All right, and when you apply a preload, that's when you first install the bolt to a specified torque, or actually a specified elongation, and we'll talk more about the details of that in a minute. Then this load that you initially apply causes a deflection in the bolt and a deflection in the material, and each one of them have their own associated stiffnesses, which is the force over the deflection in both cases. If you have the same material, this is what the graph looks like. This is just assuming the same material for the bolt and the material, but in practice, the material is often much softer. This is just for illustration. Okay, and so what's of interest actually is what happens after the preload. So this diagram shows what happens after the preload, and that is when we have our initial force Fi, that's our preload, and then we load it by P, an additional load, P. Then we have this load that's picked up by the material, and we have this load that's picked up by the bolt. And what's interesting to note is most of that load is actually picked up by the material. Okay? And the bolt, since it's in tension, it gets a little bit longer. And the material for the material, and then the material has its change in deflection, and it actually grows and absorbs that load. If you want to look at this in terms of the equation, it says that the load applied to a bolted joint is the load in the material plus the load in the bolt. The force in the material is equal to the preload minus the load that's picked up in the material. And that's, of course, if the load, the force in the material is greater than 0. If it's less than 0, then you'll have separation, and so you just would set it to 0. And the force in the bolt is equal to the preload plus the load in the bolt. Okay, so what's important to realize is that when you apply a load to a bolted joint, that most of the case, and by design, most of the load is actually picked up by the material, and this is very desirable. Okay, and so we'll talk a little bit more about that, but the point is that the material actually supports most of the load. So that's what when they say if a bolt doesn't fail when preloaded, it probably won't fail in service. Because in service, most of the load is picked up by the material. That's by design. However, if the load is large enough to cause the material to load to equal the preload, then the load of the material will be 0, and then the joint will separate, and the bolt will experience the full load. So this is the rationale behind large preloads. So if you load a bolt to its proof strength for static loads of about 90 up to about 90% of its proof strength, or about 75% of its proof strength for fatigue loads, then by design the material that it's clamping will absorb most of the loads. Okay, so this takes a second to understand, but if you kind of go back here to these different examples, then you'll see that because of, and I think this is a little bit easier maybe to see than what's in the book, but if I apply a preload, okay, let's say I stuff this block of material here, and if this is kind of abstracting, this is my bolt. Okay, when I pull this preload down here to 1,000 pounds and I put this material between it, then it takes at least 1,000 pounds to get this thing to pop out. So when you are pulling on that, the load here stays essentially the same, and the load here changes and actually is reduced by what you're pulling. Okay, so if I went up to 900 pounds, then the load here would be 100 pounds. The load here would remain at 1,000 pounds. And that's what these expressions are saying. So what we're concerned about is to make sure that when we design a system that the joints won't separate and we don't exceed the bolt stress. Okay, so we already showed that the load that's applied to a system, basically a clamped joint with some material and a bolt, the load is picked up by the material and the bolt, and the change in deflection is going to be the same for both of them. Okay, and the deflection is defined as the load over the stiffness. So the load over the stiffness for the bolt is going to be equal to the load over the stiffness for the material. Okay, so if we plug those equations back in, or we express the load of the bolt in terms of the load of the material just by multiplying both sides by KB, we get this expression. And then if we use PB in this equation, we can collect terms and get this expression here, solve for PB, and we get this the stiffness between the bolt and the material times the load that's applied. So this equation is very important actually, because you see that the load in the bolt is greatly affected by this material stiffness here. Okay, and so the load in the bolt can be much less than the applied load. This term here we call, when the materials are the same, we call this the stiffness constant, and it's represented by C in the book. And C is just the load stiffness, the bolt stiffness over the sum of the material and bolt stiffnesses. And this is in the case of where you have the same materials, and we'll treat the case where the materials are different shortly as well. But this is just to introduce that concept of the joint stiffness. Okay, so it's called the stiffness constant or the joint constant, and it's typically less than 1, which is why the bolt only sees part of the applied load. Okay, that's represented, you can see that in this equation here, right? If the stiffness of the material was 0, then the load in the bolt would be the load applied. But if the stiffness of the material is non-zero, then the load in the bolt is less than 1. Okay. So you can see that what happens when the bolt stiffness is much less than the material stiffness, and vice versa, just by looking at this equation. All right. So we can express the material load here in terms of the stiffness factor, or in terms of or the load in the bolt in terms of the stiffness factor times the load. So this is C, and this is 1 minus C times the applied load. The force in the material we can find, and that's equal to the initial preload minus 1 minus the stiffness factor times the applied load, and the force in the bolt is the preload plus the stiffness factor times the applied load. Okay, and so when the force in the material is 0, that's when we actually have separation. So we can see what happens by putting 0 in for the material load, and then just solve for the P that would cause that material load to be 0, and that's the preload over 1 minus C. So that allows us to define a safety factor for separation in terms of the load required for it to for it to separate over the applied load. So we can express that in terms of the preload over the applied load P times 1 minus the stiffness factor. Okay, so the larger the preload, okay, the larger the preload, the larger the safety factor for pullout, which makes sense. Okay, and this is just that same chart that we showed earlier. Okay, we're going to skip the examples today, but they're in your notes. This just shows you how to go through the mechanics of those equations. What's interesting though is the safety factor for separation in terms of the preload proof strength. And so you can see as you increase the proof strength, like if you're at in this example, this figure is from this example, and if your preload is 40% of the proof strength, then your safety factor is about 1. So you're going to get separation. So you have to torque that bolt down to a high enough percentage of the proof strength so that you have a higher safety factor than 1 for the designed load, so that it doesn't pull out. Okay. So that was for static loading. We also have to consider what happens under dynamic loading, and the preload is has a significant influence on the preloading dynamics of the bolt as well. Okay, so if we have a that that's applied and it's a cyclical load, then this is what we get. We get an alternating load that's between the bolt load minus the preload over 2, and a mean load that's the sum of the bolt load plus the preload, Fi. Then we can define an alternating stress, which is multiplied by the fatigue factor, which is defined down here based upon lots of empirical data and tests over the area of the bolt. And then we have this mean load here, which is KFM, which is the force, the mean force over the area. Okay, the preload is just the preload stress. It's just KFM, in this case for fatigue, times Fi over AT. So AT is that tensile area from the tables at the beginning of the chapter. Okay, so KF is defined by this equation here. Okay, so it's 5.7 plus this times the diameter if it's inches, and you use a different expression if it's in millimeters. And then this KFM is the same thing that we defined earlier when we talked about fatigue. So we look at this KF factor, and if the KF times the max nominal stress from the max load is less than the yield strength, then we just say KF is equal to KM. If it's greater than the yield strength, then we use this equation here. And typically, KFM is close to 1 for preloaded bolts. So if you look down here, this is just the force per deflection diagram for the material and for the bolt. And you can see how the load fluctuates over time. You see that the load that's picked up by the bolt, this difference in load here is what the bolt experiences, this fluctuating load here. But the material takes up most of the load. And so for fatigue applications, this is exactly what you want. You want almost all of that load to be taken up by the material so that you don't fatigue the bolt. Okay, so you don't get fatigue failure of the bolt. So this is the mechanics of dynamic loading. It's the same thing as in the static case, but the recommendation for dynamic loads is to go about 75% of the proof strength. Okay, so if you need higher stresses, then you just get a little bit larger bolt than you would have in the static case, so that 75% is still the load for the clamping force that you desire. Okay, and obviously the deflection is the same, right? The deflection in the bolt is the same as the deflection in the material, but the loads are primarily picked up by the material. Okay. Rolled threads, we talked about those last time. Those are threads that are essentially cold worked instead of cut, and it forces the grains into a certain orientation. It makes the material significantly stronger. They have significantly higher fatigue strength. So most of the high strength bolts are going to have rolled threads. Just for point of reference, when you get a bolt failure, about 15% of the failures are at that stress concentration at the fillet underneath the head of the bolt. 20% are at the end of the threads on the shank. Okay, and then about 65% are at the thread, at the nut face. So this is actually at the nut face. Okay. At the thread at the nut face. So if you have a bolt, this is actually correct. If you have the thread that runs all the way up to the nut face, about 65% of the failures of those are at that location. So the point of these slides is that the value of the preloads is significant, and you may think, oh, I don't really want to load the bolt up in this application, and we're not talking necessarily about threaded holes. We're talking about like bolts, which is a different design application. We're talking about bolted joints. Okay, so in this case, the preloads is very significant to keep those materials clamped together and to to allow that material to take up most of the load. Without preloading, those mean and alternating loads are felt by the bolt, and they increase by a factor of 1 over the joint stiffness. Okay, and since C is usually a lot less than 1, then it makes the loads significantly larger when you don't have sufficient preload. Okay, and so if you are loading your system in fatigue, then you can cause a big problem and have catastrophic failure. This is another example in the book. We're not going to go through the examples today, but it just goes through the loads. You plug in the areas, you plug in the preloads, and then you calculate your min and max, your alternating and mean stresses and fatigue factors, and then you can calculate your bolt stresses. You use your all your fatigue information for those materials, the way that it's made, and the endurance limit, and then you can get your fatigue your safety factor in fatigue, just like we did for the other applications. Okay. All right. When we talk about the joint stiffness, what we have to do is we actually have to figure out, well, what is the actual joint stiffness if we don't have this simplified cylindrical geometry. And what we really have actually when we bolt a joint together is we have this stress area here that's shown in yellow. This is a finite element method model, and this is an exaggerated deflection from the load that's applied just for visualization. Okay, now in other textbooks in machine design, they go into the details of this stress distribution triangle. Okay, but in this book, based upon Cornwell's approach, and he did 4,424 unique simulations using FEA analysis, he came up with a different approach that is described in the book that we're using for this class. Okay, so this is the more classical approach, is basically to use these geometries here underneath the bolt, but in this case we have the data from Cornwell's work. We can use that, and in his research he found that actually the bolt head deflection can actually be much greater than that stiffness equation predicts. And so if you want to include the bolt head stiffness, you can actually take your nominal bolt stiffness and you can multiply it by 1 plus that diameter over the length of the bolt to get a modified bolt stiffness, and you can express it in terms of the threaded and unthreaded areas like this from your nominal bolt stiffness, and just modify it with this equation here. Okay, so the FEA analysis used as an input the bolt diameter, the clamped length of the joint, the relative plate thickness of the two plates, and the two materials' modulus of elasticity. Okay, so in this case we're not talking about simple cylinders, we're actually talking about when we have continuous material here, and we want to find the joint stiffness value, so we have to find out, well, what is the area, what area do we choose for the area under the bolt when we have, you know, this continuous piece of metal here that's clamped between that's clamped by the bolt. Okay, and so in this approach we calculate these a few things. We calculate the joint aspect ratio, which is the diameter of over the length. We calculate the bolt modulus ratio, which is the modulus of the material over the modulus of the bolt, and we calculate the plate thickness ratio, T, which is the thickness of the lower modulus of a material, the lower modulus of elasticity material divided by the thickness of the lower modulus of elasticity material plus the thickness of the higher modulus of elasticity value. Okay, and then you can take this R here and you can plug it into this equation here, after you calculate your joint aspect ratio, you can go find your joint aspect ratio, and you can calculate your R, and you plug it in, and you can get this CR, and this is your joint stiffness when you have two plates of material that are clamped by a bolt, and the stiffness when you have the same material here, C is just equal to CR. So what happens when you have two different materials that are clamped together? Well, you have to calculate a CH for the higher modulus of elasticity material and a CL for the lower modulus of elasticity material. And then you have to calculate this CT factor here based upon another table, okay? And it uses J as well for the joint aspect ratio, okay? And you can plug that in and calculate your using your thickness ratio T. You plug T in here, okay, and then you look up your coefficient for that joint aspect ratio to get your Q naught through Q in, and then what you come up with is for a given joint where you have a high modulus of elasticity material and a low modulus of elasticity material, you get this CL and CH. And so if you plot them as a function of the plate thickness ratio, okay, then you get a line that goes between the CH that you calculate and the CL that you calculate. That's described by here, and you can see that the computed data in the fitted curve don't fully line up with this line fit, and so what's used is this correction factor. Okay, so you can use this correction factor and then plug it into this equation. You calculate your CH, which is right here, and then you calculate your CL and your CT and your correction factor, and you plug those in, and then you come up with an equation for your joint stiffness. And that C is that value here that we use here for the joint stiffness. Okay, so this, what we're talking about, is the case where we have two different materials that have long plates, and we're trying to find the effective stiffnesses. Instead of calculating the areas, we use the thickness ratio, the modulus of elasticity, the joint and the joint aspect ratio to get those values. Okay, and these equations here, this CH and the CL, they're computed using this equation here. This instead of R, where the materials are the same, we have the high and the low modulus. So we use this table here to calculate this CH and CL, and then we use this equation here to get our CT. Okay, that includes that thickness ratio. Okay, and then once we have those values, we can compute an effective joint stiffness for those dissimilar materials. Okay. So what do we do when we have a gasket in a joint? Well, there's two different types of gaskets. There's a confined gasket. Okay, so this would be like a gasket you may see in an automotive application that will go around. But in this case, a confined gasket has material all around it. Okay, and or you can have a confined gasket here, which would go all the way around it. This is an O-ring, which is used ubiquitously for sealing applications. And in this case, when you have a confined gasket, you can ignore the gasket. Okay, you can ignore the gasket stiffness because it doesn't have a significant influence on the design, because you have these materials that are in contact with each other here and here. And so the joint stiffness is not severely affected by this gasket material. That's not the case when you have an unconfined gasket, okay, which completely separates the two materials. Okay, so if you have an unconfined gasket, then you can actually calculate the effective stiffness by using these stiffnesses from this joint, from this material, the gasket material, and the base material, and just calculate the total effective stiffness using the same equation of the stiffnesses in series, and then you get a joint stiffness, okay, that's related, and this would be the material stiffness. So you'd have 1 over Km is 1 over K for the top material, plus 1 over K for the gasket material, plus 1 over K for the bottom material. And then you would use that as your Km for your material stiffness. Okay. With the exception of copper and copper asbestos gaskets, the gaskets moduli or modulus of elasticity, they're so low that they will dominate the stiffness equation. Okay. And the material stiffness can be set equal to the gasket stiffness. Okay. So for almost all gasket materials, reading between the lines here, you can basically say, well, okay, I can set the material stiffness to that of the gasket stiffness, okay, because their compliance is so much lower than the material that almost all of the change in lengths and is going to occur in the gasket material. So if you want to know how much of the area of the gasket material to use, you can use the clamp zone under a 30-degree taper from the bolt head. Okay, so if you come down 30 degrees, you can calculate that area for that bolt head to calculate the effective area of that gasket material. This is the Young's modulus for some commonly used gasket materials. You see cork, compressed asbestos, copper, plain rubber, spiral round, Teflon, vegetable fiber. Okay. This is just another example that walks you through those calculations to get your overall joint stiffness and load in your bolt. Okay, so that's what we're trying to find, is the load in the material and the load in the bolt. Okay, and I guess what's important, to note is when you have this unconfined gasket, okay, in this case, there's two different cases here I'll just point out. One is where we have an unconfined gasket on a surface, and the other one is where we have a confined gasket on the surface. Okay, so in the case where you have a confined gasket, then the load in the bolt is 581 pounds, and the load in the material is 1,775 pounds. When you introduce a unconstrained gasket or unconfined gasket here that goes through and completely separates that joint, then the load in the bolt goes up to almost to 2,000. Okay, so it's almost 4 times the load in the bolt, and the material only picks up like 395 pounds. Okay, so it's can be undesirable, if you don't want the bolt to be picking up the load and you want the material to pick up more of the load. Okay, so those subtle changes in how we put these joints together significantly affect the load that the bolt experiences. And the design philosophy is that if you get a bolted joint and you apply the right preload, that any other loads that are experienced by that joint are going to primarily be picked up by the material. Now, obviously, every design is, dictates its own solution. So it's not a universal solution to use an unconfined gasket in an application. I mean, you may not even have loads that are that high, so you don't care. But it's what you need to understand. What I want you to understand is that this unconfined gasket, it lowers this joint stiffness pretty much to the stiffness of the gasket. When you have a confined gasket, you have a stiffness in the material that's related to the material properties. Okay. So now you might ask yourself, well, okay, that's all good, but like how do we accurately get that preload, and how do we get to 75% of the proof strength for fatigue applications, or 90% of the proof strength for static applications? Well, the way you do it is you have to apply the right torque, and the most accurate method is to tighten the bolt until you actually measure the change in the bolt's length. Okay, but you may not have access to the measure both sides of the bolt, or you may be in higher volume production, or it just isn't practical for you to actually get measurements. They have ultrasonic measurement techniques and other techniques for you to get the bolt length. But it's often not practical, and so what people will use is a torque wrench, which I'm sure most of you are familiar with, and that's used in less critical applications. I would say it's used in an awful lot of applications, but you shouldn't be designing to the, you shouldn't design to the and assume that you have an accurate torque wrench, because torque wrenches are not accurate. And the estimate of the error is about plus or minus 30% of the torque that you read from your torque wrench. Even if you have a high precision, high accuracy torque wrench, you're still, the bolt preload is going to be like plus or minus 30% off. So don't spend, a crazy amount of money on a torque wrench thinking you're going to actually have accurate torque, because it's dictated by the friction that bolt experiences and while it goes into the threads. Okay, so if you take lots of care to how the bolts are manufactured, and you have high quality bolts and nuts, and you use lubrication, then you could probably get the torque down to an error range of about plus or minus 15% of its value. So, which is still quite large. Impact wrenches, which introduce significant vibration energy, so when it hits, it actually causes the whole bolts to resonate at its natural frequency. It causes like high energy vibrations. So if you use an impact wrench that has a set torque, so where it'll slip, or you use a pneumatic drive where it just stops, they are more accurate than hand wrenches, because they can get closer to that torque value, and so they're recommended instead of if you have a accurate impact wrench that has a torque stop on it, that's probably more accurate than using a manual torque wrench. But because friction is hard to predict and control between the threads, there's still large variations in the torque, the actual torque value that's present in the bolt. Okay, now we can use the equations that we developed for power screws, as you see here. Okay, and if we want this desired preload Fi on the bolt, we can use it. This is where we had the pitch diameter from the power screw, and we have the collar diameter. All we have to do is replace this pitch diameter by the nominal diameter of the bolt, and then we'll use a collar diameter that's just the average of the bolt diameter and nominal head size, which is a 1.5 times the diameter. Okay, so if we do that, which this is the average here, you see this is the collar diameter over 2. In this case, we have the nominal bolt diameter, which is D, 1 times D is D, plus 1.5, which is the outer diameter, and we divide that by 2, so that's why we have this factor of 4 here. So we use the average of the bolt diameter and the bolt head diameter to act as the collar, just like in power screws, times the friction in the collar. And then we have these two terms from the preload Fi, okay? And we have this expressed in terms of the friction and the lead angle of the screw. And we can rearrange those, and in this case we can group these terms, solve for Fi, and call all this stuff here Ki. So when we put all that together, we get this value. So then we can express the torque, the required torque to give our initial preload. It's approximately equal to Ki times Fi times D. Okay, so once we know, if we want this desired preload to get up to the close to the proof strength of the bolt, then we can use this equation to get an estimate for the torque that's required to be applied. So when you when you see torque specifications, somebody went through this analysis and said, okay, well, this is the preload that I want in that bolt, so this is the torque that I want you to apply to that assembly, so that I have that preload in the bolt. Okay. If we calculate this equation here and we assume that the coefficient of friction is 0.15, which is close to what you would get if you had lubricated threads, then you can assume that the torque for the preload is approximately equal to 0.21 times Fi times d. So if you have a sense of the preload that you want, you can multiply it by 20% of the diameter, 21% of the diameter to get the torque that you should apply to achieve that preload in that joint. Okay, and so here's a table here where basically if we assume that we have a coefficient of friction of 0.15, we can calculate Ki values, and you can see that for smaller bolts they're slightly larger, all the way up to quarter of an inch, actually 3/8 of an inch, and then they go down to 0.21. Okay, so but these are calculated values. The reality is that we don't know friction. We can't measure it beforehand. It's just there. But these are not unreasonable values to start with, especially if you have room in your design to, you can slightly oversize the bolt and get to where you have a pretty good level of confidence that you are going to be applying close to the preload that you want. Okay. All right. So there's other methods of controlling preload that are a little bit more accurate. So one of them, or not more accurate, but there's other methods of controlling the preload. One is called the turn of the nut method. This is like the old school way of doing it. You basically tighten your joint, okay, and you get down to a snug tight, and it's defined as a few hits with the impact wrench, like if you turn on your wrench and you just go let it hit it a couple times, or as tight as you can get it with a standard wrench. Okay. Now obviously we're talking about higher strength bolts. We're not talking about little tiny bolts, because you'll with a standard wrench you can pop them in two. But we're talking about like higher load bolts. Okay, so if you have these larger, higher load bolts that you're trying to get into assembly, then you say, okay, if you get it as tight as you can with the standard wrench, and obviously not everybody's going to apply the same load, but this is the method. Then you go get a longer wrench, and then you advance, assuming that the proportion of the lead you advance is directly related to the bolt elongation. Okay, so if we know the lead of the bolt, okay, and if it's a single start thread, then if we rotate around one time, then it's going to advance by that lead. Okay, so if you have a bolted joint and you get it super tight and then you go around one time, you're going to stretch that bolt related in proportion to that. Or you can use these specialty fasteners. Okay, these are called torque limited fasteners. They have a special end, they have a spline on the end, and so you come in with a special tool. That tool will grab the bolt and the spline, and then you'll apply a torque until you pop that spline off. Okay, so if you have, like say, large structural applications where you have to have precise preloads on the bolt for skyscrapers, bridges, etc., and you don't want people to be necessarily manually measuring these, and they can install these with hand tools, and you just tighten it until that bottom pops off. Other ways of doing it are with load indicating washers. So you can use a Belleville spring. We saw how Belleville springs could take pretty high loads, and they had pretty low deflections. So sometimes bevel springs are used, and what you basically do is you install them, and then you just tighten it down until the bevel spring is flat. And since you know the load that it takes to do that, then you can get an estimate of the preload in the bolt. Another way of doing it is to buy specialty washers, okay, and they're similar to the bevel springs, but they have a shape kind of like this, okay. So when you first install them, they're raised, and then you crank it down and you crush them, okay. So you smash this joint until those are crushed, and that's another way of getting an estimate of the preload. So you know that when they crush, the preload in the bolt is close to what you want it to be. All right. So one thing we need to mention is the effect of torsional stress. So although when you tighten the bolt down, what you're primarily trying to do in a clamped assembly is to keep that joint together. When you apply the torque, okay, and that's just given by our nominal torsional stress equation, the torsional stress that the bolt will see can be seen here in this Moore's diagram, okay. And so when you're applying that load, when you're torquing that bolted assembly down, you get this shear stress that develops in the bolt, and that increases your principal stress, okay. So it makes it higher because you have a combined loading event, because you have the axial load on that bolt plus this tensile, this shear stress that you're applying when you torque it down. So what happens though is this torque that you apply, that causes this shear stress, this torsional shear on the bolt, it actually can go away. So you can relieve this stress by, after you tighten it down, to back it off without loosening it, and that'll relieve some of the shear in the bolt, or it'll be relieved over time through vibration, or just while it's in service. It's well known that this shear actually relaxes. So when it relaxes, the preload actually goes down, or the state of stress in the bolt actually goes down. So that's why they say it's like, if you don't break the bolt when installing it, it'll likely survive the loads for which it was designed, because when you're installing it, you're actually introducing a state of stress that's higher than it'll experience after that shear stress is relieved. Okay, that torsional shear stress is relieved. Okay, and I guess the point is like, when you're installing the bolts, the torque is not going to be super accurate, off by like 10 or 15%, and if you just go from that, the stress is actually relieved. Okay, so that torque value that you measure is not going to be the same that it experiences because of this relaxation. Okay. All right. So that covers joint stiffness and bolt preload, and the effects of installing it with a torque wrench or other application. The next thing that we have to talk about is what happens when the fasteners are in shear, which is often a case. Okay, so in structural applications, you'll see these all over the place, for beam and beam connections, bridges, etc. You also see rivets and welds as well, and I still encourage you to watch the videos that I made about that, which are long and slow and painful, but have good information. Okay, and so in this case, when you preload these bolts, you torque them down, you actually create large frictional forces between these plates, and those frictional forces are beneficial in preventing shear. Okay, so if you have an applied load and these bolts are torqued down really well, then the material is going to pick up the majority of that shear stress. Okay, if you don't have enough friction though, then the material doesn't pick up that shear stress, the bolts pick up the shear stress, and you put the bolts in direct shear. Okay, so it's another reason why you want to have sufficient preload, is to also get the material not to take up the load, the axial load, but to also get the material to take up the shear load, so that shear is not experienced by the bolts. Now, if you're doing more precise work and you're assembling a machine, bolts are not the best thing for you to use to locate parts. Okay? And instead, people use dowel pins, and they're all over the place in machines. Okay? Dowel pins do two things for you. They help take up the shear loads, but they also help in locating features, so that when you assemble and disassemble on a machine or assembly, that you can locate the machine with sufficient tolerances. Okay, so for example, tolerances of 5/1000ths of an inch. If you want to assemble a machine and you really need these tolerances because of your application, you can't have any slop, then you can use dowel pins, and then after you get everything where you want, you can install dowel pins, and then bolt it together, finish bolting it together. Okay, so dowel pins, they're helpful because they're very hard and they can resist the shear loads, but they can't handle any tensile loads. And also, it's very important to note that bolts and screws are not made to tight tolerances generally. Okay, and bolts are used with through holes. Okay, so you have to put the bolt through the hole, and it's larger than the bolt. So it's not a good idea to necessarily use bolts to locate things in your design if you have to have any sort of high accuracy or high tolerance. Now screws, even if you have a threaded hole, you cannot guarantee concentricity. Okay, so the center of the hole and the center of the screw are not going to be perfectly concentric with one another. Screws will be eccentric. Okay, so if you need a precise application and you imagine you can, and get everything to line up perfectly, and you're just using bolts and screws, you may be in for a frustrating experience. Okay. And so what people often use is they'll use, dowel pins. Okay, this is an exaggeration of the tolerances. So here's two bolts in a joint, and you can see that the bolts fit through fine, but because of the tolerances of these holes, there's a lot of play. Okay, and if you have external loading or vibration, then these things can actually also move relative to each other. So a strategy to prevent that and to make sure everything is where you want it to be is to put a dowel pin smack dab in the middle of these two, so that you get it where you want every time, and then you use the bolts to provide the clamping forces to prevent shear and axial loads. And if you design the preloads right, then the material is going to take up those shear and axial loads. Okay, so this just shows an example where you have a better design. So this is your initial design for this plate here. Okay, and if you need any sort of accuracy, then you can have a design like this, which is a lot more accurate for locating. And it takes up a lot more. It takes up more of the shear. Dowel pins are real cheap too, and you just pop in two more holes. There's a little bit more work involved in putting in the dowel pins. Okay, so and that's we talk about that here. So dowel pins are actually made with tight tolerances, typically 1/10 of a 1,000th of an inch. Okay, they're hardened and ground, and they're truly round. Okay, they're available in a lot of different materials. Okay, so you don't need some super hard, high strength dowel pin if you don't have those loads in your system. You just need them for locating. You can use some low carbon steel, corrosion resistant, chrome steel, brass or alloy steel. They're cheap, okay? And typically what you'll do with a dowel pin is you'll press fit it into one part and then close slip fit it in the other part, okay? And you remember we said the press fit, we had the machinist rules of thumb where you multiply the diameter by 1 or 2 thousandths, or whatever the unit is, 1 or 2, 0.001 to 0.002 up to a certain diameter, and then you go slightly larger for larger ones, larger diameter bolts, but you can create a press fit. Okay, so you can hammer the or press with an arbor press or other type of clamp. You can press to fit the dowel pins, and then you'll put that in one part, and then you'll close slip fit on the other part. So you have a real high tolerance interface. Okay. So dowel pins are often added after. They're not always added after, but they're often added after assembly. And so what you can do is kind of bolt everything together, and then when the structure's been aligned to where you want it to be aligned, okay, then you can drill the hole, pilot the hole first, drill it, ream the hole for the press fit on the bottom part, and then ream the hole for the slip fit on the top part, and then you can install your dowel pin. Okay. So if without dowel pins or welds, then machine assemblies can slip due to those larger bolted holes. Okay, with dowel pins you can have accurate and repeatable assemblies. Okay, so the last thing we're going to talk about, and also something that shows up on every PE exam that I've heard from other people taking it, it's in the PE book, is how do you find the loads in a fastener? And it may not be super obvious at first. And so the question is, I have a load here, and I have this bolt group here that also has some dowel pins. And the question is, what is the load that each one of these bolts is going to experience? Okay. And so the way to solve this problem is actually to take the centroid of the bolt group, so we can find not only the forces, okay, here, and in this case we have two force components. Well, the first force component just comes from the static force. So we basically just take this load and we divide it by all of them, right? So the first force that we get is this applied load over these 3, 6, 8 different bolts and dowels, and that's the force that we get on each one. The magnitude of the force due to the moment, okay, is this F2, and that's where we have to have knowledge of the centroid of that bolt pattern, okay? And this is the way that we do that. We can look at the weighted area of each bolt. So AI would be the area of one of these here. XI would be the X distance, if this is X and this is Y. It's just your centroid calculation. Okay, so we would do that for each one, from 1 to N, where N is the number of these fasteners. So I take this guy, I multiply its area times its distance in the X coordinate. I multiply this guy times its distance, which is going to be 0. This guy times its distance, which is also going to be 0 for the X direction. And I get this guy, and it's going to have a negative X component. Okay, and I sum all these up, and I weight them by the area. So I divide by the area, and I can get the centroid of this object. Okay, so they all are symmetric. So obviously, the centroid in this case is going to be in the middle. That's often the case for a lot of these textbook problems. But if you have them separated and or more spread out for a different bolt pattern, then obviously you have to calculate the centroid. It's not as obvious, but in this simple example, it's obvious that it's in the middle. We do that for the X and the Y. We find the X and Y coordinate, okay, and then we can find the distance to that individual bolt, which is the moment arm, R, okay, to that arm. And in this case, all the R's are the same. because they're the same distance for the moment. And we can calculate this force, which is the moment here, which is the load times the length to the centroid. Okay, and then I divide it by the weighted distances here for all the bolts that are in that area, and I can find it for that particular bolt. Okay, so once we have this stresses, we can find the resultant force and divide it by the area of that bolt and find the shear stress, and we know that the shear strength is about 57% of the yield strength. Okay, now this is what the bolt pattern looks like. Okay, so this shows the F1 and F2 and the resultant force F1 and F2. In this case, they cancel out. They cancel out. And then in this case, we have these loads, so we have this resultant force. And in this case, we have this poor little bolt over here that has twice that force almost. Okay. Okay, so this bolt that's closer here is going to be experiencing twice the load, and that's because of the direction. Okay, so this load tends to cause this downward force, but that load in this bolt pattern causes it to rotate in this direction, which causes a force that's opposite. Okay, so those forces oppose each other, and then this bolt here experiences twice the load. When designing bolts, should we design them as dowels first and then decide the specifications for a bolt? No. So basically, you want, if you're trying to keep two materials together, then it's just like all the other applications where you calculate the loads that you expect for that particular application, and you want to make sure that those loads don't exceed the the loads that the bolts can handle or the loads that the material can handle. And so I mean, if you're designing a clamped joint, I mean, you'll design it to have to have those clamping forces from the bolts. The dowels are there for accurate locating and to help prevent shear. Okay, but they don't help you with the clamping force. So I hope that answers your question. This is a table here for the minimum strengths for dowel pins that are in double shear, okay, like this. Okay, and for low carbon steel, they're about 50 for the shear strength. For alloy steel, about 117. Corrosion resistant 82, and brass about 40. Okay. So you will see this again, and this is important. All right. So we will end there, and I want to ask if you have any questions. So I don't see any questions. So this is our last class. I just want to thank you for your attention, and I wish you all the best with the rest of the semester. And I hope you get some much needed rest and relaxation. It's almost over, and I will post the test tonight or tomorrow morning. I do not Yeah, I will post the slides right now. I do not anticipate the test to be as long as some of the other tests because I know that it's late in the semester. It'll be more just some more practice for the applications and shouldn't be too involved. So, all right. Well, thank you guys for your attention. And if you have any questions, just send me an email and I'll post the slides right now. Thanks.